Hello from my side as well. I'm Esther. I work for Bitkom as Sebastian does. And I'm the host for the second part of the afternoon here on the stage. I'm really looking forward, and I would also like to introduce my first speaker, or our first speaker here on stage, Professor Wolfgang Maaß. I think he's already here and ready. I'm using the time and will introduce you to the audience. Professor Wolfgang Maaß is the scientific director of the German Research Center for Artificial Intelligence, as well as a professor for business administration and a co-opted professor for computer science at Saarland University. His presentation titled Quantum Computing for Simulation in Manufacturing. And, oh, you're looking for something for a presenter? Maybe? Do we have a presenter for him? We lost it on the way, but there it is. So, Professor Maaß, stage is yours. I'm leaving.
Okay. So, hello everybody. I just learned that I should have brought in my whole team for filling in the gaps that I cannot fill. So I'm representing quite a complex project called Quasim. We are investigating how to improve simulation processes in manufacturing by the help of quantum computing. This is a project funded by the Federal Ministry for Business Affairs and Climate Action. Okay, so we have two use cases. One use case is milling. That means milling, in this case, a blisk that is part of a jet engine out of a titanium block. And if you do that, you realize that you do it in the wrong way. It starts to vibrate, resonance, and then you have these scratches in this metal piece, and titanium is quite an expensive metal, so you can throw away a whole thing. So that means we want to investigate how can we determine by simulation what are the resonance frequencies and how we can avoid them. The second use case, I mean, Friedrich Struckmeyer was on the panel a couple of minutes ago. We are working with Trumpf, which is a use case where it is about laser cutting, and the laser cutting machines from Trumpf are exceptional. But if you want to run them 24/7, sometimes the design of the piece that you cut out of a metal sheet is, let's say the whole setup is not perfect, so that you have too much thermal energy into the production process, and then the pieces get stuck, and you cannot get it out of the metal sheet. And if you have a 24/7 production operation, and something happens in the middle of a night of Saturday, it's bad. So therefore, in order to predict thermal expansion, we also want to investigate whether quantum computing can help. Current situation in manufacturing is a lot of trial and error, independent of what you hear on the theoretical basis, what you can do. It's a lot of trial and error, even with highly sophisticated and large companies. On the more theoretical side, we can model a lot. We can apply finite element methods and other kind of methods, and the current trend is to introduce also artificial intelligence into the whole manufacturing process and simulation process, in particular convolutional neural networks, but this is in the making. The outlook is now the question about quantum computing, and the promise of quantum computing is that quantum computing will help a lot. Boston Consulting Group has a prediction that if you are a first mover, you will have a huge advantage, while laggards will suffer from not getting hand-on talents, suffering from loss in market shares and other kind of very important effects on your business. So therefore, in our project Quasim, we are investing all these kind of questions that you see on the lower left side, which is, can quantum computing help? Is it practical? And can we combine it with something that is already getting into the operation, namely artificial intelligence? And the hypothesis is that on the numerical side, quantum computing can help, and as well as integration with machine learning. At this point, I want to say I'm not a physicist. Yeah, so I think that here always people say I'm a theoretical physicist. I'm not. I only have a minor in physics, so bear with me. Okay, so finite element method, because that's a core of simulation. Yeah, this is in the end easy to understand in the end, yeah, because if you have a gas, but in our case, if you have a solid object like a titanium block, you chop that into pieces, geometric forms, you define the physical laws in between, and then you start simulating. If you introduce a force from the outside, how will it react? Yeah, and then you can see in the red, the visualization is always very important. You see whether there is something that you have in force, or whether it's red in our case if there is a strong vibration, a strong resonance. So you can solve that with traditional differential equation, partial differential equations. But there are also theoretical proposals to do that completely with quantum computing. Never has done that before, yeah, in practice, but theoretically, yeah, Montanaro and Pallister have proposed that. And another way is a little bit around that, is to try whether you can get from both worlds, that you have something that is from a classical world and something from a quantum computing world, more in a hybrid. Okay, so what we are investigating is then the two routes. On one hand side, combination of quantum computing and numerical approaches in the case of the milling use case. And the second route that we are investigating is the laser cutting use case, where we combine quantum computing and artificial intelligence. Okay, so first, the milling use case. This is what you see on the left side. This is what happens if it resonates. Yeah, you have cutter locations and you do some cutting, and if it starts to resonate, you get some deep scars, yeah, some scratches in the metal. Yeah, and because the tool is rotating with high speed, these scratches can become quite deep, and then the surface is rough. Yeah, and for a turbine jet engine, this is not acceptable. So what you want to have is a low vibration production process, so that the surface is, I mean, not for a microelectronic microscope, yeah, then it's still kind of rough, yeah, but this is in the tolerance. This is where we want to go, also related to noise, yeah, but just to get an idea for that. When we started with that, we started with what the people, especially from IPT Fraunhofer at RWTH Aachen, investigated for decades, how to produce such kind of jet engine blades. Okay, and what they do is they identify cutter locations where they cut out the titanium, and you only see 8. Why 8? Because the traditional computers cannot simulate more. Yeah, it will exceed computational capacities. So therefore, it's a rough approximation of this anyway. And this is brought into a Dexel representation, which is a 3D representation of the object. And then you take the matrices for the masses and for stiffness. These are the major matrices that we will see in a minute, that we bring into the finite element method, do the simulation, and what you then see here are these phase representations. These are the points with the frequencies you try to avoid. These are the frequencies that you want to have. Yeah, so you want to find the windows of frequency where milling is doing okay. So what we then did is we did the formalization on the mechanical engineering part, yeah, and we started very simple with simple oscillators. Yeah, what you learned in high school already, but you transform that into differential equations. You have mass, you have stiffness matrix, yeah, and what you do there is you transform that into a characteristic equation, yeah, where you want to where do you want to identify the eigenvalues and eigenvectors, and if you have the eigenvectors, eigenvalues, they are related to the natural frequencies of this compound that you have, because we have more than just one object that is starting to oscillate, because The finite element method dissects everything in thousands and millions of objects. Yeah, so they are all oscillating in 3D. So therefore, what we want to investigate, what we want to investigate is to find the natural frequencies and the mode shapes here, so to identify in particular the frequencies of high resonance. Okay, then the physicists step in and they say, okay, you're engineers, we understand, yeah, how this works, and they have also a different notation. Yeah, we'll come back at the very end, yeah, to translate that. But the mass matrix and the stiffness matrix is the same, and they also do the thinking of translating that into a characteristic equation. It took us quite a while in order to translate that into this characteristic equation in order to extract the Hamiltonian here, the Hermitian matrix that you want to identify, and here we have the frequencies squared for the k objects that we have. Okay, and then in the end, if you transform that back to x, because here is, let's say, an approximation to make it simpler to read. But in the end, what you want to have is you want to have the frequencies for all the entities, the physical entities that you have that start to oscillate. Okay, and this here is the matrix we are interested in, the response matrix according to the frequencies that we plug in, and we want to identify the eigenfrequencies. By doing that, I mean, the natural approach for doing that is quantum phase shift, and this here is a well-known ansatz to use that. You have here, let's say, an approximation, initial approximation for your eigenvector that you plug in at the beginning, starting with ket 0 vector. You put that into a superposition state, and then you have some unitary function operators, and these operators use HP, which is the matrix that we constructed on the slide before. Okay, and what this here is doing is that we still always keep on the unit sphere, obviously. Okay, so we transformed everything from the partial differential equations into a quantum representation in order to, in the end, by using the quantum phase shift model, in order to identify the eigenvalues, which are in our case the eigenfrequencies squared that we have, and we also get the eigenvectors that are related to these eigenfrequencies. Okay, so that was, in a very small nutshell, what we are currently working on. We are by far not finished, yeah? But this is, we are 1.5 years in the project now. The second use case is laser cutting, thermal expansion, and the question is, can we make a prediction on if a laser cutting head is moving along a metal, how the temperature is expanding? The approach that we are taking here is we have different ways that we are investigate in parallel. A purely quantum approach, but the most promising one is a hybrid approach where we use a graph neural network approach and combine that with quantum approach. Okay, so how does it work? On one hand side, we have the mesh representation. Yeah, so this is where we start with MATLAB representation. We construct the adjacency matrix, we construct a graph neural network approach, and we make predictions. So where is quantum computing coming in? Very simple. We use an approach that is published by Seth Lloyd and colleagues, especially those from Xanadu, because they said, okay, let's investigate machine learning from this perspective of quantum embedding, because quantum embedding, the embedding part is already the part where you have the nonlinearity that you need for neural networks. The rest is linear in quantum computing, so it's not helping you for machine learning. So the interesting part, Seth Lloyd argues, is getting here in the variational encoding part. And this is what we are leveraging. We take the data here, x, y, z coordinates plus temperature, only 4 qubits, yeah, and we do a node encoding. And this node encoding translates back into the data that we feed back into the graph neural network representation. And we take a variational approach for this so that we train this embedding till we have the right type of embedding. Okay? And what we found is that this embedding here, if you do the embedding with, it's hard to see, we compare it with 3 different embeddings, with a multi-layer perceptron that has the same number of neurons like the quantum approach has qubits, or 2 to the power of the number of qubits. Yeah, so this is what we compare, and what we can show is that the embedding with using the quantum approach, that this is comparable to a neural network that has 2 to the power of number of qubits neurons. So that is a tiny little advantage, yeah, but it shows us where we can practically integrate a large problem or integrate quantum computing into a very large problem. Okay, very briefly, what we are working on right now is to enhance that with a physics-informed approach, where at the end, after the neural network approach that I just showed, that we also make a prediction on physics laws, and this even helps us to accelerate and improve this whole process. Down there you see the simulation of all the different types of neural networks, quantum enhanced neural networks that we have, and so far the results are quite promising. Outlook at the end. I mean, there were some talks about how to integrate that in practical contexts. That is very important for us because we want to, in the end, we want to have services that are served to engineers on one hand side, but also to maybe some other decision makers that also want to work with such kind of simulations. Yeah, so decision makers that we are working on. And what you see down here, also to leverage several kind of libraries, and we are fortunate to have access to both quantum computers in Germany. And that brings me to my very last slide. The summary is, in our laboratory setting, with a lot of theory, it works. Yeah, on Penny Lane, especially we are using Penny Lane. Other team members are more based on Qiskit, but we are good on our path there. The hybrid quantum computing approach is really helpful to bringing together some effects on quantum computing with machine learning. So that is also something where we developed quite some confidence that we at least get certain results. The last part is system modeling. The system modeling is very challenging because you have the modeling of an engineer, you have the modeling of a physicist, a theoretical physicist, and you have the modeling of a computer scientist. And then you have the modeling of somebody who comes from the outside and says, I want to see the business. Getting that together is really a challenging task, and I think that is worth investigating because we will not have enough theoretical physicists in the future. Yeah, so that is definitely something we have to look at, especially if you are looking for students alone. Okay, Outlook. We are currently preparing the first run on the IBM system in Eningen, and it's not 100% sure whether we will also do the experiments on a D-Wave advantage system, but let's say I'm positive that we will make it. So that's the team. Without the team, you're nothing. So these are the people who it's really a fantastic group of people. Yeah, I mean, we have people from FZ Jülich, from IPT Fraunhofer Aachen, from ModuleWorks and from Trumpf. It's a great team, and all kudos go to those people who are there on this picture. Yeah, with this, I thank you for your attention and open for questions. Thank you.